Welcome. Today we're going to introduce logic, so a new topic. It is not in the textbook. That's okay. So all we'll have are these notes and everything I tell you. So, logic sounds simple, but it's not. So, logic is based on propositions. Okay? And so a proposition is a sentence where you can assign a true or false value, and that's it. Okay? And so, for example, 4 is even. That's true. Now, I will introduce immediately for true, we tend to use a 1, and for false, we use a 0. Okay? You are allowed to use, um, if you want to use true and false like that, you can. It's just usually ones and zeros are a little bit quicker to write, a little bit easier to read. Okay? And so I encourage you to try the zeros and ones where 1 is true and 0 is false. Okay? And so, but you are allowed to use T and F if you want to. Okay? So, for example, a proposition can be something like 4 is even. That, I would say, is true. Today, it is raining. I can tell you it is not. So, in this case, today, it's false. Yeah? It's still a proposition, right? We can still assign a true-false value. And the last example of a proposition, we have math class today. Well, sort of, because you're watching this video, I guess. So I'll say it's true. Here you are. Okay. So often what happens is we connect these propositions, right? And so we can make compound propositions using words like and, or, not, if then. So if something happens, then this happens, and if and only if. And so what we can do is we can create a larger proposition using these connectives. So we need to know how these connectives work. So if you have two propositions, okay, then what happens is your first, where am I here? Yeah. If we have two propositions, I lost my way. If we have two propositions, then each of those will have two possible truth values, true and false. Right? And so that means that there will be a total of 4 ways that we can rearrange all the possible truth values. Okay. And so what we find, or what we will find, is that the most convenient way of doing this and arranging these truth values is with a truth table. Okay. And so we'll be working a lot with truth tables, and so we need to know how they behave. We're going to start with the word and, right? Which is also the first word in our list. It's a really common connective, right? And so technically it's called a logical conjunction, okay? But really what we mean here is and, okay? We tend to denote propositions with letters such as P and Q. So we start with P for, I presume, proposition, and then P, Q, R, S. Those are all kind of common generic ways of denoting a proposition. So if P and Q are propositions, okay, then their conjunction, P and Q, now notice when you read this, and we can say is an A, which you can say, or I shouldn't do equals because that is special, right? But what we have is we denote it by this kind of upside down V. I don't know how to this. Okay. And so notice that if you draw a line here, it makes an A, right? And so then you can read it as and. And so it's just shorthand for and. Okay. We do need to, or I need you to be able to read these symbols. Okay. And so they might take a little bit of practice, but soon enough you'll have them. And there aren't that many. Okay. And so if we have any generic proposition P and Q, what we do is to set up our truth table, we have these two columns. Okay. What we do is we start with P because it's first in the alphabet. Okay. And if we have only two propositions, right, P and Q, then we know that there are four possible combinations. Okay? Four, and I divide that by two, that means I start with two zeros and two ones. Okay? And then what I do for the next column is I alternate 0, 1, 0, 1. Now what we'll see is that you have 0, 0, right? Both P and Q are false. Okay? 0, 1, which means P is false, Q is true. P is true, Q is false, and then P is true and Q is true. Okay? Now together, these are all the possible combinations of P and Q. Okay? So let's write that here. This is all possible truth combinations, or I'll say truth value combinations of P and Q. Now, if we're talking about P and Q, okay, then for P and Q, this combined statement to be true, right? The only way that that can happen is if they're both true. Okay? So how we denote that, and let me see here. P and Q is only true if both P and Q are true. Okay? So our truth table is going to look like this, right? If P is false and Q is false, well, then P and Q, a statement combining the two, would also be false. If we move on to the next line, P is false, Q is true. Well, if we have a false statement in there, the overall statement is still going to be false. Okay? Same thing, if we swap them, P is true, but Q is false. Well, one of those is false, so overall this statement is false. Okay? But then if they're both true, then we get a true value. Okay? Now, like we said, I stole this from a different textbook, and it's a little harsh sometimes how it reads. To read this truth table, you must realize that one line represents a case, so that's fine. It's one possible set of values for P and Q. Okay? And so each line represents a case. Okay? Now the numbers 0 and 1 are used to denote false and true, respectively. We already established that right from the get-go, but it's nice to have it here. And the order in which we list the cases in a truth table is standardized. Okay? And so I always want you to start with zeros. So you list half your zeros, and then the other half is ones for the first one, and then you alternate. Okay? And this this goes back to binary digits, and we're not going down that road, but it's nice to do it properly. Okay. What's another conjunction that we can have? Well, we can have a logical disjunction. Okay. And so this is going to be or. Okay. P and Q are propositions. Their disjunction, P or Q, which we denote with it looks like a V, a capital V. Okay? But notice how the and was basically an A without a line in the middle, right? And so the or is the upside down version of that. And that's really the only way that I can um, remember those. Okay? Or the V makes an or. Okay? And so now, what's nice about or, for or, only one of P or Q needs to be true. I'm missing an S here. Needs to be true for the overall statement to be true. So what that looks like, I'll draw a line down here. We've got the same setup, 0, 0, 1, 1, 0, 1, 0, 1. P or Q, well, if they're both false, P or Q is still going to be false. Okay. But now notice that if at least one of these is true, then the overall statement is true. Okay. And so 1, 0 still makes 1. And of course, if they're both true, then the overall statement is true. We can negate things, of course. This is going to be not. If P is a proposition, its negation, not P, is denoted by, and I'll zoom in here, is denoted by this kind of hook P. Or if you prefer a tilde P, that's fine too. I'll use this little hook, okay? And I just read it as not P. Okay? Now, of course, if you only have one proposition, P, right, it only has two truth values, zeros, one. Okay? And not P is, of course, the opposite. Right? And so if P is false, then not P must be true. And if P is true, then not P must be false. Okay? We're ready for the next level, I think. About these propositions, I'm going to quit if I don't get a raise. Okay? If I pass the final, then I'll graduate. I'll be going to the movies, provided that my car starts. All three of these are conditional. And so they can all be restated into the form if some condition, then some conclusion. And so what we're going to do is we're going to rewrite each of these statements into a if this, then this format. Okay? And you'll see why that's going to be important in just a moment. Okay. So I'm going to quit if I don't get a raise. Now, in the if-then format, right, this becomes if I don't get a raise, then I'm going to quit. Okay? So if I don't get a raise, then I am going to quit. We can say that this can be a proposition P. I either do get a raise or I don't get a raise, so it's either true or false. And I'm going to quit could be considered another proposition. which is either true or false. Right? Oh, oh yeah, here. I was going to write conditional statements here. There. If I pass the final, then I will graduate. Now this one is in the right format already, so I'm happy. Huh? The next one's a little tricky. I'll be going to the movies, provided that my car starts. Now, it's understood that this means if my car starts, then I'll be going to the movies. Okay? So it takes a little bit of work, but if my car starts, then I will go to the movies. I changed the wording slightly, right? Technically, I'll be going to the movies, then I will be going to the movies, but I changed it to I will go to the movies. There's a little bit of flexibility as long as you understand that it has to be in an if-then situation. Okay. Now, a conditional statement, if this, then this. Okay, so if P, then Q, is meant to be a guarantee. Okay? If the condition is true, then the conclusion is expected to be true. Okay? And that's it. Now, a conditional statement, in terms of a truth table, well, first, in terms of its notation, I guess we should start there. Okay? If P, then Q is denoted like this. Okay, and I'll highlight it and kind of zoom in here. If P, then Q is how you're going to read something like this. So you have a little arrow between the two, and so you have if P, then Q. Okay? We can look at our table of propositions. We've set up our table the same way that we did before. Now we have two propositions, of course, because we have to start at if P, then Q. And so we have 0, 0, 1, 1, 0, 1, 0, 1 to cover all our possible combinations. Now what happens, and this one is really the only, I would say, tricky truth table to remember. However, what you'll see is that the only false combination of P and Q, so if P then Q, is this one here, where we start at a true value and we go to a false value. Okay? Otherwise, all of these are ones, right? They're all true. Going from a false to a false. Okay? Going from a false to a true is still true. And of course, if they're both true, then it's true. Okay? Now, as an example, and I've cheated and I have written out the example below, but let's do an example that looks like this. If your instructor told you, if you receive a grade of 95 or better in the final exam, then you will receive an A in this course. Okay? Now what I've done down here is if you receive, so here's the statement, the conditional statement, if you receive a grade of 95 or better in the final exam, that's going to be P, right? You either do get a 95 or better or you don't, right? True or false. Then you will receive an A in this course. And let that be Q. You either get an A or you don't. Okay? So if you fulfill his condition, right, you get 95 or better, then you expect to be getting an A because that's what he said. Okay? Now, if we translate our P's and Q's, right? And so here, what does a P being 0 mean in this case? It means that you didn't get 95 or better on the final exam, right? And so here, but then you didn't get an A as well, right? And so that's true. You're okay with that as a student. You would say, well, he didn't lie, right? And so you didn't get 95 or better, and you didn't get an A in the course. Okay? So that's still true, right? He didn't lie. How about if P is false, but Q is true, which means you didn't get 95 or better, but you got an A in the course, right? Because your other grades maybe worked out to an A overall still. Okay? So you're still happy, right? It's still a true statement, right? You're able to get an A even if you didn't get 95 or better. Well, it's harder, but you can. How about the third scenario? Now, you wrote the exam, you did get 95 or better, but then he didn't give you an A. That's false, right? He's a liar. Huh? You would say, hey, you said if I got 95 or better, which I did, right? I was supposed to get an A, right? And so that's why this one is false. And if they're both true, I got 95 or better, and I got an A, I'm happy, all right? So that's the reasoning behind the only one being false is if you go from a true statement to a false statement. Okay, so in a conditional statement. If we consider this conditional statement again, if you receive a grade of 95 or better in the final exam, then you will receive an A in this course, right? We can write that as P. So if P, then Q. Now, what we're going to introduce are three variations of this conditional statement called the converse, the contrapositive, and the logical inverse. Now, if you go to your formula sheet, which I don't have right here, hopefully I'm on here. If you go to your formula sheet and look in the logic section, I've given you these. Okay? And so you'll have these, but you need to be able to read them and translate them. Okay? So what are they? We start with the converse. The converse of the proposition if P then Q is the proposition if Q then P. Okay? So how you're going to read this is you break up your statement, your conditional statement, you find your P and you find your Q, and then you reverse them, right? And so you're going to read them as if I receive an A in this course, then I got 95 or better on the final exam. Huh? And so this is the converse. There is some flexibility in the wording. You're allowed to just keep it exactly as it is, even if it doesn't sound very nice. Okay, that's totally fine. Or if you think you can find a nicer way to say the same thing, then that's fine. Okay. One thing to notice, so if I get an A in this course, then I got 95 or better on the final exam. Now that doesn't have the same meaning as the original statement, right? Because we already established that, hey, I'm able to get an A without getting 95 or better on the final exam, right? That's a possibility. Whereas this statement says, if I get an A in the course, then I must have gotten 95 or better on the final exam. And so notice that if P then Q is not equivalent to if Q then P. It's a different statement. It's the converse. Now, there is a proposition related to if P then Q that does have the same logical meaning. And this is the contrapositive. The contrapositive of if P then Q is this proposition. How you read this is if not Q, then not P. Okay? And so you're going to negate Q and P and use them in your conditional. If I do not get an A in the course, that's not Q, right? Then I did not get 95 or better on the final exam. Okay? And so that is equivalent to the original statement. Okay? Just two different ways of saying it. There's a third variation of if P then Q, and it's called the inverse. Okay? Now the inverse has the same logical meaning as the converse. Okay? Kind of similar to how the contrapositive had the same meaning as the original. Now the inverse of if P then Q is if not P, then not Q. Okay? If I did not get 95 or better on the final exam, then I will not get an A in the course. Okay, so on a test, what I expect you to be able to do is take a statement like this, right? A conditional statement, find your P and your Q, right? And then I'll ask you to write the converse, write the contrapositive, and write the logical inverse, right, in words. And so that's why I give you these guys here on your formula sheet. And so these are only helpful if you're able to translate the original statement into if P, then Q. I forgot I don't have a pointer in here. So it's going to take some practice. So let's see. We're going to write the converse, the contrapositive, and the logical inverse of if it snows today, then we have the day off. So here, P, if P, then Q is the order that we need it in. And it's missing a little arrow here. So if P, then Q. So now I've determined what my P is, what my Q is. Okay? And so now I need to remember that, okay, the converse from the formula sheet is if Q, then P. If we have the day off, then it snowed today. Okay? Now I encourage you to try these without, maybe pause and try these, but you know how to do this. The contrapositive from the formula sheet is if not Q, then not P. Okay? So if we don't have the day off, then it did not snow today. And the logical inverse from the formula sheet, if not P, then not Q. If it does not snow today, then we do not have the day off. Another example. We want to, again, write the converse, the contrapositive, and the logical inverse of I will do well in all my courses if I study. Okay? Now, what's important here is that you first rearrange this statement into a if then statement. Okay? And so how it reads is, if I study, then I will do well in all my courses. I'm going to drop that just for simplicity, okay? But it's understood. So I encourage you to try these on your own, but the converse will be, if I do well in all my courses, then I studied. The contrapositive will be, if I don't do well, then I did not study. And the logical inverse will be, if I don't study, then I will not do well. Nice. So like I said, I encourage you to try those because I just read them out. Okay. Our almost the sort of last idea to introduce is called the biconditional. So we had the conditional if then. Okay. Now, of course, the biconditional becomes if and only if. Okay? So again, if P and Q are propositions, okay, then the biconditional statement P, if and only if Q, is denoted by this double arrow. Okay? And so this double arrow is essentially if P, then Q, and the other way around. Okay? And so that becomes the double arrow. And we read this as P if and only if Q. Okay? Now, if we look at the truth table of this thing, okay, I've built it out already, you'll notice that it's only true in two cases. In fact, the only two cases are when P and Q are the same. Okay? So notice the biconditional is true when P and Q have the same truth values. Okay? And what we can do is we can build out this truth table to confirm. So here we're told what the final truth values should be, but we're going to confirm that with a truth table. Okay? If P, then Q, remember, this is just a single conditional. It's only false if I start at a true and I go to a false. Okay? And so here, false to a false, well, that's true. So I write 1. A false to a true, that's true. This one, true to a false, no, that's false, right, from earlier. A true to a true makes a true. Now, for Q, so if Q, then P, I want to read it the other way. So now I have to start in my Q column and go to my P column, right? And so 0 to 0 is a 1. Okay. 1 to a 0 is a 0, right? Starting at a true, going to a false, that's false. Okay. 0 to a 1, that's true, and 1 to a 1 is true. Right, so we have these here. Now the biconditional, notice says if and only if. Okay? And so that's the clue. Okay? Because now, if you consider P, so if P then Q, as one proposition, right? It's a compound proposition, but that's okay. It still has some truth values. And if Q then P as another proposition, right? So we've built these out a little bit. If I look at the and of these two, what do we remember about and? And has to be true for both values, right, in order to be true overall. So here, this first column and the second column, well, they're both true, and so the overall statement is true. If I have a true and a false, the overall statement is false. A false and a true makes a false, and a true and a true makes a true. Okay? And so notice how this is the same as what we were given in the original table. Okay? But I tend to remember it as, okay, the biconditional is really only true if I'm going between the two same values, 0 to 0 or 1 to 1, right? And then it's true. Okay. In terms of terminology, now there's a kind of a separator here. All the following are equivalent to if P, then Q. Okay? Saying P implies Q, Q follows from P, P only if Q, Q if P, P is sufficient for Q, Q is necessary for P. I'm not going to test you on these. It's just good to be aware that these alternate phrasings exist. Okay? And all of the following are equivalent to P if and only if Q. P is necessary and sufficient for Q. P is equivalent to Q. This one we will use. So keep that one in our back pocket, probably for next day. If P, then Q, and if Q, then P, right? Kind of a nice broken down version of what we just saw. And if P, then Q, and conversely, right? And back again. Okay. What if we have these propositions? P is going to be Fred likes Cindy. Okay. And so I like to just put P above here. Okay. And Q is going to be Cindy likes Fred. Okay. We're going to use the connectives, and let's practice reading these. And, or, not, if then, and if and only if. Fred and Cindy like each other. That's the same as saying Fred likes Cindy and Cindy likes Fred. So that's going to be P and Q. Fred likes Cindy, but Cindy does not like Fred. Okay. And so this here is the negation of Q. Okay. And so we need not Q. Fred likes Cindy, and Cindy does not like Fred. That's the same statement. Okay. So Fred likes Cindy, and Cindy does not like Fred. Kind of confusing, I know. Fred and Cindy dislike each other, which means Fred does not like Cindy, and Cindy does not like Fred. Wait. Fred likes Cindy, or Cindy likes Fred. Well, that's P or Q. Remembering that Cindy likes Fred is Q and Fred likes Cindy is P, then if Fred likes Cindy, then Cindy likes Fred, right? Remembering that you have to have your if first, right? Then that translates to if P, then Q. Okay. And Fred likes Cindy if and only if Cindy dislikes Fred. Okay. Fred likes Cindy, that's P. And Cindy dislikes Fred is not Q. And if and only if is the biconditional. Right? So P, if and only if, not Q. Okay. Those take some practice. I think we're ready for a true truth table. If we have what we call a compound proposition C, which looks like this, okay? So let's read these, and we're going to be mindful of the brackets, right? So P and Q, or not Q and R. Now I have three propositions, okay? And so I've got P, Q, and R. Okay. Each of the three simple propositions has two possible truth values. And so what happens is there will be 8 different combinations of truth values. Okay? If I have 3 propositions. For us, it's just a matter of remembering that you have 8 lines in your truth table. Okay? Because what does that mean? It means that if you list your P, your Q, and your R, you're going to start with 4 zeros followed by 4 ones, and then alternate 2 zeros, 2 ones, 2 zeros, 2 ones, then 0, 1, 0, 1, 0, 1, 0, 1. Okay? And that will ensure that you have all your possible combinations of the truth values. Okay? So, what I want to do first is set up P, Q, and R in my table here to show you. Okay? The biggest truth table that I will ask you to do is going to have 3 propositions. It's possible to have 4, but it just becomes too big. That would be 16 lines, right? No thanks. And so, let's see here. I think it's 16. We don't go that far. So I have 8 lines. Okay. I wonder if I can, I'll just do it. 0, 0, 0, 0. So 4 zeros first. Okay. Then I list 4 ones. All right. Being nice and methodical about how you list these, right? Because there is a proper order. Then inside the zeros, right, I split those in half for the Q's, and I have 2 zeros, 2 ones, and then for the ones, I split them in half as well. Zeros, ones. Looks like this. 0, 0, 1, 1. Then I start over. 0, 0, 1, 1. And then for R, I alternate. 0, 1, 0, 1, 0, 1, 0, 1. Notice that these are all different combinations of truths and falses, right? In fact, it covers all the different combinations. Okay. So, what we want to do is we want to end up, our final column will be all of these things linked together. Okay? But I do see that I can find P and Q first. Okay? So let's start here. Call this A. Or maybe I'll just call it, label it green. So here I have P and, oops, Q. I read it as and as an A, but I wrote A. Oops. For and to be true, right? And notice, so here I can ignore this R column for a little bit because this only involves P and Q, right? And for and to be true, I need them both to be true. Otherwise, it's false. And so I go through here and I see 0, 0, 0, 0, 0, 0. And then finally, I have both of them being true. And so that's the first time that this P and Q will be true. 1, 2, 3, 4, 5, 6, 7, 8. Okay. You read the brackets just like you do in math, right? And so what I'm going to do is I'm going to consider this next set of brackets not Q and R. Now, if you're comfortable negating Q in your head, right? Flipping it from a 0 to a 1 and a 1 to a 0. You're allowed to do that, but what I prefer to do is I prefer to make a fresh column of not Q, okay? Just because it's going to be easier to read. Okay. So here, not Q. Then I'm going to look at my Q column and I'm going to say, okay, well, it's going to be 1, 1, 0, 0, 1, 1, 0, 0. 1, 1, 0, 0. And 1, 1, 0, 0. Try to keep my spacing here. Let's see if I can just draw some lines real quick here. Otherwise, it'll be a real mess. Nice. Okay. So now what I want to do is I want to build this out. So now that I have not Q, I can look at not Q and R. Right? Not Q and R. Let's see here. Let's use light blue. Not Q and R. As long as one of them is false, it's all false, right? And. So they both have to be true in order for it to be true. I have a false R, so that's false. Here I have a 1 and a 1, so finally we get a true. Not Q is 0, R is 0, that makes 0. Not Q is 0, so even though R is true, the overall statement is false. 1, 0 makes 0. 1, 1 makes 1. 0, 0 makes 0. And 0, 1 also makes 0. Okay. Notice that the only thing left is this or. Okay? Because now I have my green column or my blue column. Now remember, for or, as long as one of them is true, the overall statement is true. Okay? So finally, we can find P and Q, or not Q and R. But really what we're doing is the or of the green column or the blue column. All right. So, or, as long as I see a 1, it's 1. It's true. This or that. Okay. I see 0, 0, that makes 0. 0, 1 makes a 1. 0, 0 makes a 0. 0, 0 makes a 0. 0, 0 makes a 0. 0, 1 makes a 1. 1, 0 makes a 1. And 1, 0 makes a 1. Aha. This is the truth table for this compound proposition C, right? C is this thing. Okay. And so what this tells us is all the combinations of P, Q, and R that yield a true statement if you've combined them in this particular way. Okay. That's our first truth table, and we'll practice more next day. But I think they're pretty fun, and once you get the hang of it and kind of working and building them out methodically, then they'll start to make some sense. And 3 propositions is as big as we will go in this course, and so you don't have to worry about going further. But in general, if C is generated by n simple propositions, so in this case there were three, then the truth table will have 2 to the power of n rows. Okay? And with the first n columns being an enumeration of the n-digit binary integers. And so here, binary is just zeros and ones, and so these represent um, different numbers. In fact, 0, 1, 2, 3, 4, 5, 6, 7, 8, um, which computers use to read logic. Okay. Now, there is some hierarchy, just like BEDMAS. And in math, we have BEDMAS, brackets, exponents, division, multiplication. Division and multiplication are on one level, right? It's the order that they appear. And then addition and subtraction, again, is on the same level in the order that they appear from left to right. Okay? And just like in BEDMAS, the parentheses or the brackets override any of the BEDMAS order. Now, in terms of logic, the first thing you're going to do is the negation, okay? Which is kind of what we did up here, right? I said, hey, it's going to be hard to negate this in my head, so I'm going to deal with this not Q before I find not Q and R. Okay? Then the conjunction, which is and, okay? And is multiplication essentially, okay? And or is addition. Okay? And we'll see that again when we do probability. Okay? Fourth, we do the conditional operation, and then finally we do the biconditional operation. Okay? Within any level, we work from left to right. Okay? And so what we see is if we have P and Q or R, okay, because and comes before or, then we read it as first I have to do P and Q, then or R. Okay? And so this is, of course, what computers use to read logical expressions. Okay? So if you have to use parentheses to clarify the order of these operations, okay, remembering this order here, then if we have P and Q and R, okay, first you do the P and Q, then that and R. Okay. For the next one, not P or not R. Remember, negation is done first, so I'm going to put brackets around the not P and the not R. So I have to do those individually, then do the or of those. How about not P? I know, funny. First you have to negate P and then negate it again. It cancels out. Okay. This one's tricky. Last one. First, we look for any negation. Right? I don't see any negation, so I move on. Then I look for any ands. Because I have an and in here, how I read this is I need to do Q and R first. Okay. I don't have any disjunctions, no ors, okay, but I do have a conditional operation, okay, which means that first I need to find Q and R, then I need to find from this column if then S, okay, and then finally I can do the biconditional, okay. And you can set up the truth table for this, but I think I'll save it for next day. All right. Uh, Great work. And we'll keep practicing our truth tables next day. See you. How do I stop this?